Hello everyone, I am Seren. Today we will be talking about the effect of hot isostatic pressing on fatigue behavior of particle-reinforced aluminum matrix composites which are processed by laser powder bed fusion. We will start with introduction and define what AMCs, aluminum matrix composites, are, and shortly discuss laser powder bed fusion and hot isostatic pressing. After material and processing details, we will have a look at the microstructural analysis and discuss mechanical characterization results and conclude today's presentation. Aluminum matrix composites are composite materials produced by the incorporation of high modulus reinforcements into aluminum matrix. In our case, we will be using ceramic particles as reinforcement. When these ceramic particles are introduced into aluminum matrix, several strengthening mechanisms can be activated, such as the load transfer through the interface from matrix to ceramic reinforcement, hole patch strengthening thanks to smaller grain size, Orban strengthening due to dislocation looping around the ceramic particles, and increased dislocation density because of the coefficient of thermal expansion mismatch. And all of these allowing high strength and stiffness to weight ratio. AMCs can be produced by several methods, and laser powder bed fusion is one of the most promising alternatives. LPBF is an additive manufacturing technique in which powder is spread and fused selectively by the laser, and scanning continues layer by layer till the whole part is completed. Thanks to its intrinsic properties, LPBF is advantageous for AMC production. It can enable homogeneous distribution of the ceramic particles, flexibility of design, short interaction time, which would mean less reaction time between the ceramic particles and the liquid aluminum, and finally high part density thanks to subsequent local melting. However, as you all know, pores such as lack of fusion pores or gas pores are common process-related defects in LPBF parts, which can be detrimental to fatigue life, as the pores would act as cracked nucleation sites and lead to premature failure. And therefore, HIP is commonly used as a post-processing for critical parts to improve density. It applies high temperature and pressure, helps reducing the porosity, but it also causes microstructural changes and decrease in strength up to 50%, for example, in the case of aluminum silicon 10 magnesium LPBF parts. In this study, we used aluminum silicon 7 magnesium 06 as the matrix and mixed it with 1% nanosilicon carbide to produce our composite powder. And here you can see in the SEM image nicely decorated composite powder. And for production, we used SLM Solutions 280HL with the 160°C base plate preheating. We built vertical and horizontal samples, which we will be comparing in the coming slides. And afterwards, some samples were tested in as-built conditions, while some samples were subjected to HIP treatment, of which you can see the parameters here. And all the samples were machined prior to testing. Here you can see the optical microscopy images of horizontal and vertical as-built samples for the microstructural characterization. And the values are representing the average Archimedes density values, showing slightly higher density was achieved for horizontal samples as compared to vertical samples. And here you can see the optical microscopy images for horizontal and vertical HIP samples presenting increased density for the HIP condition. As you can also see in the reconstructed micro-CT images on the right side, much lower overall fraction of pores is observed in the case of HIP as compared to as-built. And in this graph, it is shown that in the case of HIP, no pores larger than 90 micrometer was found, so the large internal pores are eliminated after heat treatment. In here, in this SEM image, ultrafine as-built microstructure is shown, and if we zoom in, fine silicon precipitates within the primary aluminum grains, which are surrounded by aluminum silicon eutectic network, can be seen. Also, by TM, it is shown that silicon carbide reacted with liquid aluminum and formed aluminum carbide in our case. And for the HIP condition, we observe a much homogenized microstructure, dissolution of eutectic network, and coarser silicon precipitates. When we have a look at the EBSD maps for as-built and HIP samples, no significant grain growth is recorded after HIP, which can be due to the grain boundary pinning of nanoparticles. Here you can see the relative density and hardness values for horizontal and vertical samples in as-built and HIP condition. While there is no difference in hardness between horizontal and vertical orientation, HIP treatment resulted in much lower hardness values for both. And when we have a look at the tensile test results, we can again see that tensile behavior also of horizontal and vertical samples are very similar, except for higher elongation of horizontal samples in the as-built state, which can be related to the porosity amount and the orientation. There is a decrease in yield strength around 34% due to the dissolution of eutectic network and coarser silicon after HIP, while elongation increases significantly thanks to reduced porosity. Here you can see the ascent fatigue test data for horizontal and vertical samples in as-built and HIP condition. Overall, horizontal samples, which are represented by the squares, are located more towards to the right, showing better fatigue resistance as compared to the vertical samples, which are shown by the triangles. This can be explained by the void orientation being perpendicular to the loading direction in the vertical samples. And when we compare as-built, the blue ones, with the HIP condition, the red points, we can see that HIP samples have higher fatigue performance as they run for a larger number of cycles compared to as-built samples at the same stress levels. Since the grain sizes were similar, this can be attributed to the poor elimination thanks to the HIP treatment. Finally, fractal graphs of as-built and HIP samples are shown here and is marked in white in figures A and C. As-built samples have more pores visible at the fractured surfaces, while dimples suggesting ductile fracture are observed in all samples at the below pictures. When we have a closer look at the as-built samples, we can see that lack of fusion pores or subsurface pores acted as crack initiation points. So we can conclude as the following. No considerable effect of building direction was recorded. Horizontal samples were slightly better than the vertical samples, and this can be attributed to the porosity orientation being perpendicular to the loading direction in the case of vertical samples. And as for the effect of HIP, after the treatment, dissolution of AM ultrafine microstructure was observed, eutectic network disappeared, and coarser silicon precipitates were there. Ductility increased significantly thanks to the closure of big pores. Decrease in yield strength and hardness was recorded, but the decrease in yield strength was limited to 34% only. And finally, fatigue performance was improved thanks to higher density and similar grain size for HIP samples as compared to as-built samples. Thank you, and please feel free to contact if you have any questions.